September 3rd, 2025. We got a new wood stove setup, and I'm going to go over how it works. On the bottom here, we have the secondary airflow. It goes in under the stove and comes out at the top of the firebox. I've got a couple of holes on the riser tube to give more primary air in the back of the stove. On the left, we have the control box, and that's operating the two fans. The second fan is the primary air fan. It's up on the top left there. It's putting in that plenum tube, and then it goes into the top of the stove. This particular stove has vents right above the door, and we have to put air in there. Otherwise, the fans push it out those vents, and that's why I had to put that plenum tube on there. And then on the back is the convection air that pumps air behind the stove and out the top, and we were getting 125 degree air today. This is the secondary air fan. It puts out around 7 CFM at max, and it is modulated. This is the primary air. It puts out a max of around 4 and is important to keep the flames yellow. It is also modulated. They both spin up at the same time. They just put out slightly different amounts of air, and they also put air in different locations into the firebox. Part of our instrumentation suite is this Dwyer Mark II. I have it zeroed at 0.05 because sometimes it can go negative a little bit. This helps me keep track of the fans and if they're putting too much air pressure in or if the exhaust system is pulling too hard. Today is 9/11, and that's a sad day in our history. However, I did some testing today, and the system is working great, but I'm trying to tune it in. So I'm going to do a series of videos Explain Like I'm 5 and ELI5. And I'm going to go into more remedial or basic knowledge type information because I've been doing a lot of testing and videos for the people at Berkeley, and college students are at a different level than the average people. So I'm going to work on an ELI5 and go through the graphs if I was explaining it to my kids, my grandkids, or something like that. So that's what this series is. I did a 5-hour test on the system, and I have the two charts that are important to me up on the screen. The top one is opacity, which is the legal metric for smoke measurement, and it's on a scale of 0 to 100%, with 20% being the critical point where if you exceed 20% opacity for 6 consecutive minutes, that is essentially illegal and you can get a ticket for that. So that's the reason we measure opacity. It's also a good way of determining how much smoke you're putting out. It doesn't tell the whole story, it is the legal metric. The other line on the chart, the top chart, is color shift. Now, it's easy to measure. It's easy for me to measure. It's got a numerical value that comes up. What we don't know is what does it tell us? And we have people working on that, and we don't have a great answer. In my opinion, it is the fine particle ratio to the normal size particle ratio. So when particles are under 500 nanometers, they scatter blue light, which shifts the visible light received by the sensor into the red. And so we're measuring that color shift, and that is the red line. On the bottom, we have 3 graphs. The orange line is the stack temperature. So there's a thermocouple, a temperature sensor in the stack, and it is recording every 5 seconds. It is a measure of the stack gases, which are normally going to be very high, but you can see at 1 hour and 15 minutes, and then again at 2 hours, there's some dips down. That's when I open the door and let cold air through, and you can get a register of every time I open the door. So stack temperature is the gases in the stack, which when you open the door, cool off. The blue line is the shell temperature. I've got a thermocouple, which is a temperature sensor, bonded to the top plate of the wood stove. So it is essentially the same temperature as the top plate of the wood stove. And it stays rather constant. The green line is the heating air. So there's a fan that blows air across the back of the stove and over the top of the stove. That tends to run around 120 degrees when the stove is up to temperature, and that pushes a lot of air out into the room and it warms the air in the room. This is why we have wood stoves. We can turn a few pounds of wood into good usable heat. I've put on the chart now from 2 hours to 5 hours. So this isn't the full set of data, but I can tell you what I did during this time. The first peak at 2 hours and 15 minutes is a half round log that is around 1 kilogram, 2.2 pounds. Very dry, let's say 11% moisture, and it's put on top of hot coals. The air control system then figures out new fuel's been added and starts adding fuel. It ended up burning this one log in the wood stove all by itself. The fire in the background is not this log. I didn't have any cameras set up. On the bottom graph, you see that the stack gases stayed fairly constant near 400 degrees Fahrenheit. And the temperature of the wood stove stayed fairly constant around 275 degrees from 2 hours to 3.5 hours. So we get an hour and a half or 90 minutes of heat out of one log being controlled by an algorithm that keeps the fire going and keeps the stove at a fairly constant temperature. The heating air, the green, is putting out 110, 115 degree air for 2.5 hours. It's a great system. A wood stove that's controlled puts out very little smoke, and it also keeps the wood stove at a constant temperature where it does burn clean.
Where warmth is key, a secret hero works to keep the air free. No smoke, no fumes, just clean and bright. Our smokeless chimney shining with delight.